Hello boys and girls. In this video I want to quickly talk about set builder notation, which is the sort of informal notation that you nevertheless see everywhere, used often without any explanation, when concepts are formalized informally with logic or with some first order logic, second order logic, and so on and so forth. Since in the last video I went through a proof where I freely used, let's say, first order logic language, I think it will be good if I summarize some of the notion and how to read them, how to translate them to a formal version of themselves, right? So the way I approach the videos up till now, and certainly also going forward, is that I try to tend to give the explanations as they are stated formally whenever it is feasible. So I would say my presentation is a little bit stricter than in most books, let's say, in that sense, but not as formal as in a theorem prover. And so when you, for example, use some dependently typed language to do math directly, yeah, with the Curry-Howard isomorphism that I talked about a year ago or so, then you're using one language which has terms that reduce and compute stuff. But if you use, for example, let's say first order logic, then in principle you have a logic at hand which just makes statements about sentences and derivation of going from one sentence to the next. And for example, if you imagine the set that contains the elements 3, 4, 5, then there would be a term corresponding to that object. But in all statements that you make and everything that you prove, you don't formally just write down the set in the ether and this object stands there on its own. No, you make statements about it by formally binding it into some sentence with a lot of quantifier maybe and connectives and so on and so forth. And so in this video I want to explain kind of how to translate these objects when they pop up into actual formal objects. The bulk of the video will be about different examples of set builder notation, and at first I also want to talk about different logics, because as I said, different logics understand these objects differently, especially on the constructive side. I try to get the most constructive aspects out of my proofs as possible. For example, as you saw in the last video on this no-go theorem, as a result of some fixed point theorem, there is some, let's say, computational content. There is some terms that you can construct, and so I tend to use, at least I try to use a constructive logic. If I can, then stick to everything intuitionistically. I mean, I don't pull through because I also want to elaborate on and use concepts that are not as constructive. But effectively, everything you can prove in, say, a first order logic, you can also prove in an intuitionistic version, even if the sentence is constructively speaking not the same. Classically, they will, and so you can get very far with a little bit overhead, but then you have it easier if you want to implement stuff. Okay, I'm ranting here. I talked a little bit about these things also in a rant format in my video on what are non-classical logics. Let me just quickly browse through again a bunch of Wikipedia pages that tie to this video. So there is of course a Wikipedia article. Approaches it from various sites. This might be maybe a little bit more basic than what I do in this video. Maybe not. As I said, there are different logic calculi, and essentially we're just, in my videos, I'm generally sticking to classical first order logic. It has uncountably many subsets, or it has a lot of subsets, and also different modes of actually proving things, different rules of inferences. And so here is one page, if you're interested in that, discussing various derivation calculi in this Hilbert format, where you basically just have modus ponens and a lot of axioms. And so there's a lot of to get out of, and it tells you, like, if you study those, then you get a lot of these logical equivalences that also hold true in first order logic. So this is one thing. Nevertheless, if you do proofs, then they often look more like, oh, this is the video, this is the paper I pointed to last video on the diagonal construction. Let me actually close that. So, sorry, I wanted to say, if you actually do the proofs, then they might look more like a natural deduction, or even sequent calculus. This is also a related proof calculus. So this is another, let's say, mode of proving things. You can use these frameworks for different logics. But how you go about it differs, and I suppose, I don't want to put my hand in the fire for that, but I suppose most of the proofs will look more like natural deduction. You also have this nice name, right? Natural deduction. Okay, so I will in this video not explain it in any detail, but then just pointing out there are different logics and frameworks, and so the things I'm going to discuss today is going to be used by me for first order logic with an emphasis on intuitionistic logics, but there's more, and so whether or not the statements that I make on equivalences that I discuss hold will strictly depend on the logic calculus. This is my point here. So we start out with some propositional calculus, where we just have statements that might be true or false, at least in the Boolean versions of them, and that has then the nice Wikipedia page on the weaker quotes and quotes logic. And here you also, if you scroll down there, have some of the equivalences that classically will often go both sides, but constructively, if you study the connectives, will not go on both sides. And so just if I do some proofs in these videos, and you would like to understand that, or understand why I don't do certain things, because I want to stick it to a more constructive framework, you can of course ask in the comments, but also like just going through these pages and these references on the Wikipedia pages might help. And I'm pointing now to some sites where there are some listings of these rules as well. Okay, so there's minimal logic, which looks very similar to the intuitionistic logic. It has some weaker aspects to it, but in many cases, if you do an intuitionistic proof, it will also approve in this system. I just pointed it out because I like it. First order logic is where you already also have the predicates and quantifiers. And lastly, let me point to, there's this table where different rules are linked to and explicitly discussed, and especially in particular, if you look to the universal quantifier page, let me see, universal. I'm searching for the universal quantification page, and here this has also a lot of these rules about how to rewrite expressions, especially with no, let me actually check the existential one. I think that's the more elaborate one. Yeah, here's some discussion about negation and so on. We will also touch on this in this video. So I would say this is really worth reading. Classically, there's a lot of equivalences, and you get by with just a few objects. constructively you cannot get that far with so few objects. There are things that are strictly different and not equivalent. So this is the point I want to make here. Okay, so let's move on from the browser and get to this short text that I quickly want to go through, right? So first half is going to be just some points on logic and notations that I use also regularly, and later on the set builder notation. So in this text, I will have some propositions, that have some truth value. It's raining. I read a book today, and so on and so forth. This will be ABC. And then some term symbols. So we're going to have a predicate logic where we reason about things. In our case, and in the foundations of math, usually in general, your terms are just sets. You have a theory about sets. And so these are term symbols. In our case, this will be sets, predicates, and then variables that you can quantify over. I would say the most harmless of the connectives is the conjunction. By the way, I will not dwell on this too much today because, for example, in the video on implementing connectives and showing equivalences in the classical propositional calculus, I discussed this here 7 months ago. So if you're interested in more like basic logic, go back to that. So we have and negation, for example, flipping true to false and false to true. And classically, you can take those and express all other connectives with them. So there's the entailment or implication, then or the disjunction, and you can find equivalences on them, and then the B implication. Constructively, the negation is a little bit difficult, the disjunction as well, so there's fewer relations, and I try to avoid them usually. But okay, so here this is like the B implication is almost always used like so. And if you have a classical logic, then we can, for example, say the disjunction is built up from negation and conjunction by flipping the negations twice. This might be very basic, but I will come back to that also in the quantifier case in a moment to show you some analogies there. Similarly, we could also go in the other direction. We can start with disjunctions and define the conjunctions, and this extends. Then you can easily show that it extends if you have a finite amount of propositions. You could, for example, express it like that. And then in the predicate calculus, we have existential quantification and universal quantification. Classically, you also need one of them because you can use a negation to flip between them. Constructively, this is not possible, and so there's a point to be made whether you want to, like for example, if you have a statement which involves one quantifier and a negation, you can switch them and switch between quantifiers, but it might not be, like you might lose some constructive strength, let's say, if you use one or the other. So if you want to capture more information in some statements, then I would watch out for that. Okay, so then there's the slash through a bunch of symbols, for example, for the existential quantification. This is used, and I used it actually in the last video, where you just negate the existence. If you are in a constructive framework, then the negation, as a side note, if you have a statement like, let me write this here, negation of A, right? Then this would possibly also just be a shorthand in reality for A implies false, where false is a logical constant. Or in some frameworks, like if you look, for example, at the calculus of construction, which is the base of the Coq proof assistant, there you, for example, have the negation expressed not with a constant, like it not n doesn't mean that not a doesn't mean that a leads to an absurdity, but here similarly this is defined by saying that for all other proposition, if not a would hold, then a would imply any other proposition. So this has the same effect in the sense that once you prove the bottom, once you prove the absurdity, then you basically like failed, or then it's the end, and by the principle of explosion, then you can derive anything, right, from absurdity follows everything. So this has the same effect. So you see how in different calculi all these things might be differently implemented. So let's let this here. So okay, this is as a note. And so, for example, to elaborate on where this negation relations come from, also for the quantifier, I suppose this should be clear to most people. So, for example, if I say at least one of them is true, today is Saturday or today is Sunday, right? Then this is the same as saying, classically anyway, it's not the case that it's not Sunday and not Saturday, right? So if we rule out that both of those are false, then at least one of them is true. The other direction is even easier, like to comprehend anyway. If I say today I ate breakfast and lunch and dinner, then classically this amounts to saying the same as it's not the case that I didn't eat one of those, breakfast, lunch, dinner. So if it's not the case that I left anything out, then I had all of them, right? So, and I'm making a point here again to emphasize that the quantifiers, even though they might range over an infinite domain of discourse, like over all sets, over all group elements, if you have a finite domain, then you can think of these quantifiers also expressed with conjunction and disjunction. So, for example, let's say P is a day I love, and let's say I love Saturday and Sunday, then to say, and Saturday, Sunday and Friday, and then to say there is a day that I love would hold true, and it is true by, let's say I love Saturday the most, right? Because either of, like, for among all 7 days, if I love one day, which is Saturday, this statement is true if one of them holds. And so this, you have here this disjunction. I'm just making these examples up on the fly. I hope this is pretty clear. Like if you have this existential qualification and you say, oh, there's at least one which validates the proposition P, and so this is the same as just listing them, in which case the domain would be just 3 elements, ABC. And from this relation that, like similarly, you can say, if something holds for all days, for like for all weekdays I have to work, then it's the same as saying there are 7 weekdays, so the domain of discourse is 7 days, Monday, Tuesday, and so on. So it's the same as saying on Monday I have to work, on Tuesday I have to work, on Wednesday I have to work, and so on and so forth. So if the domain is finite, then the quantifiers really you could consider them in some frameworks anyway to be just a shorthand for this finite length, this disjunction, conjunction, right? And from this relation stems this classical negation flips also. So you can read it that way anyway. So if you say for all days I have to work, then this is classically equivalent to saying it's not the case that there's a day where I not have to work, right? So it's not the case that they were not have to work, ergo I have to work all days. And so you see, this is really just a relation that we had here. Okay, again, I'm pointing this out. Classically, everything like falls together. You have very few fundamental ingredients that you need. You can define a lot of other ingredients. I don't say which ones you will have to read, for example, the Wikipedia article on intuitionistic logic, but some of them might hold, others might not, right? There's the fact that these equivalences don't always go both ways if you want to stick constructively. And maybe in a video I will give more examples to how you can see that. Although I'm only, like you're seeing, I'm hasting through this video, I'm already going too long. I try to make these videos shorter while being self-consistent to some extent. So let's pass on. Okay, so finally we come to set theory, and set theory is in virtually all axiomatizations just first order theory of one binary predicate, the membership predicate, right? So you have this element of this symbol in the logic, like added to your signature, as you say, of these logics, and all that you do is make statements without variables, and from the axioms of logic and the set theory and the inference rules, you derive new statements. So everything that you will be proven is a statement, and therefore, as I said in the beginning, we will have to we want to actually make sense of what does it mean to have this object, right? This is not a sentence. This is one term. It's not a statement, and it's not even part of our logic axiomatization as such. It is basically notation, and so I want to explain what does it actually mean, and how you, when you read these sentences, how you must translate them if you want to be as formal. Okay, so let me just point out some abbreviations. So similar to the existence, if you say there doesn't exist something, then you say this slash through the existence, and with the is element of, you also have this relation with the negation. Okay, it's not small x is not an element of capital X, where these are both term symbols, then or variables if they're in a sentence. If you quantify over them, then we just need this one negation. Okay. If you read such a bounded quantification, then this is also here just shorthand for this statement. So you do a conjunction of this claim about membership, and make brackets around it, and the proposition that you claim. So if you read this, really this just translates to that, right? So here in first order logic, there's really just there exists of and for all, and this is always going over the whole domain. And so if you see that we just go over all elements of the set, then this is not actually something you do. You never actually scan over just the elements of a set, at least in these formulations that we present here. But you always scan over all, but in those cases where this is not element of the set, you have here a false, and then the whole thing is false, and then therefore it's never seen by the statement, so to speak. But in reality, the quantification formally goes over all elements in the domain of discourse, over all sets. And similarly, we have the implication if we have the or quantifier here, and you might, similarly to the end, you might think about why that makes sense that this is an implication here. So next, a quick note on the subset symbol. I talk about it just because I will use it in the next video on the Cantor theorem and the diagonal argument. This is, like, let's say, our first introduction of a new notation, and to some extent discussing objects using set theory is about the subset relation, right? In set theory, like in axiomatic set theory, you have this a nested universe of sets and sets and sets. But when you use sets, let's say in practice for various reasons, you're usually interested in putting other elements into sets that are not sets themselves. So it's not just about sets. It might be a bunch of numbers in a set, for example. And so it's very often the case that you want to express actual relations in terms of subsets and not of membership, actually. But nevertheless, the theories are theories of the membership predicates. The axioms are all for the membership predicate, and so the subset relation is only expressed in terms of that. And here, for example, if you have a bigger subset, a bigger set Y and a smaller subset X of Y, and by bigger and smaller here, I don't mean cardinalities, but just which elements are in the one and not the other. Then if I write here this equivalent symbol, in that case I just mean whenever we read that, like formally speaking, you would actually replace all occurrences of this binary subsentence with this fuller expressions, a fuller expression, and this is an expression that is really just in the pure logic calculus, right? All the symbols are fundamental to our notation, so we discussed that these are in our language and we choose them freely, and then we have brackets. Okay, I didn't discuss any brackets here, but it's kind of straightforward. And then the actual symbol for which the axioms of the set theory reason about. And it says, for example, that if little x is in capital X, then that means that x must also be in the big one, and in that sense it's a subset, right? We define this relation. Okay, and then finally let's go to the actual set builder notation or set notation, right? So for example, we might have this expression, right? And this round brackets, the set notation expressions, are not actually part of the formal language as we set it up, because it's in set theory, for example, it's really just the is element of symbol that defines this predicate of whether or not an element is a member of a set, and there is no talk about round brackets, right? This is notation, really. And so this, if you have that this term A is an element of that set, where that set is all x such that P of x holds, well, then one implication is definitely that A has the property P of x. So this is, you can replace that statement really with the content of just saying P of A. What I want to emphasize is that not everything you can write down can actually prove to be a set, right? You have then the axioms of specification and separation. Axiom of separation. That are in terms of a predicate and tell you something about the existence. I will not dwell on this axiom so much, but they give you a rule which predicate can actually be used to show existence of some sets. So just because you have a predicate doesn't mean you can form the set, right? So for example, you might express a property is an ordinal number, for example, but the collection of all ordinals in your theory may not be a set, and so it's a little bit dangerous here in this case that you might end up confusing yourself. So you can translate this down here, but if you want to be formal and if you want to be let's say explicit or overly explicit, then I just want to point out that be aware what you're doing here. So another notation is not is element of, but is equals. So equals is also an usually element already of the logic with all its laws, like reflexivity and so on and so forth. And you can see how this translates to that statement right here. Let's say here is a constant term, a particular set. Let's say natural numbers, for example, right? So some symbol already being defined to represent another set. Then to claim this is to claim that the elements from this X all fulfill this property, right? You can see how this applies. And I didn't write it down, but if you have something like that, if you have to claim that two sets are equal, two predicates, right? What does this claim? Well, easy to see that makes sense to read it like so, right? For all the elements hold if they have these property, then they also have this property. I want to emphasize again, this notation on the left hand side, they are not really part of the theory. We might introduce them and give a formal meaning to them. I'm very weak in my statement here, just say claims, and claims is just, you know, a common language word. I don't want to set any equivalences, because actually if you do, in principle, set theory, you don't actually need these notations at all. You can always stick to these right hand sides, which are actually in your language. And again, coming back to what I said in the very beginning, this all depends on the logic framework that you actually want to work in. If you have a type theory where you have lambda expressions, where the meaning of the expressions themselves already are weightful, have some content to them, then you might actually have a theory of where you introduce sets, where you introduce expressions that are just round bracket objects, and it's meaningful to talk about them. But here in first order logic, we don't have them actually in the language, and we can only give the meaning as we go along. We have, similar to the quantification, if you have this notation, so previously there was just this X on this side, now I plug in more stuff on the left hand side. This is similar to the existential quantification, right? And similarly, if you have here some construction, like f, some function, let's say, function expression, function body, then you can think about how that all works out, right? We go to the last part and give some examples. So let's say we have here, this is what I'm going to use in the next video actually. If A is an element of this set, where what does it say? Well, it says all elements in this set have this form. For all elements here, there exists a Y such that X is actually a singleton containing the Y. If X is in that, well, that's just mean that A is a singleton, right? So this really makes this claim here. So this is an example of that here, where the P is the whole thing here. Similarly, if we define Sy, as an example for that here, well, then that says that if X is in this Sy, then the same property hold, right? Here's another example with this subset predicate, and then lastly, what did I do here? So let's shortly discuss about this. Let's go there at the end. Let me speak about this. I call them ad hoc notations, where we, for example, say 1 to 3 with these commas, right? So I mean, obviously it's easy to translate that, but here this is basically a set. You can translate it like that. You can say, oh, for all X in X, this holds, right? All X here are either 1, 2, 3. Similarly, you can translate it to X equals, like let's actually do that. So we can also say that means X equals all X such that, so, right? So you can see that, but in this case I had to translate this notation directly, and if you have, for example, write down here this expression where you leave things out, and you can make use, for example, of this function expression to to capture that. But usually you will know on the fly how to translate this kind of formal finite syntactic expressions like this here. Like there's a scheme there to know what it is, but I guess that's kind of obvious. Yeah, similarly here I use now some of those sets to give an example for use of this notation. For example, here all x in the range to 7 that are even, and that will filter out something, will end up like this. Similarly, here's this function that I already used here. In this case, I just start after 9001. Okay, so the takeaway lesson is here, like there are ways to translate these things, and if I write down, if you use those, then really I have some normal logic language expression in mind, and this in the context that we are using, just going to note these kind of things. Okay, I hope that wasn't too lengthy. I didn't want for this to take half an hour, but I will certainly refer back to that in future videos. It's good to have this written down. Things maybe that are usually not talked about as explicitly as in this video. So take care.